All right, in today's office hour, I plan to talk about outliers, leverage points, and influential points. Um, then I'll briefly talk about the F-test for the regression model and the partial F-test. I think this section is rather important, and I hope you guys will get a chance to watch the recordings. Okay, so first, I will follow the example I made from last week. It's still a regression model to predict the win percentage of NBA teams. However, this time I'm using a multiple linear regression model instead of a single linear regression model. Again, my predictor, instead of the field goal percentage, the C3 column, which I used last time, I add some more potential predictors, including like 3-point field goal percentage, the free throw percentage, assist, turnovers, offensive rebounds, defensive rebounds, and something more. Those are my potential predictors because intuitively I think those statistics might be helpful for predicting the win percentage of a team. And after some model selection process, which I want to select like which predictor to use, I come up with a 5 predictor model. I want to use the field goal percentage, which is the predictor I used from last week, but also I'm using the 3-point field goal percentage, the turnovers, steals, and defensive rebounds. I'm using 5 predictors together to predict the win percentage. So that is multiple linear regression model. Using the same steps, I go to stats, regression, fit regression model, and my response, which is the y, is the win percentage, and I have 5 predictors: the field goal percentage, 3-point field goal percentage, also using turnovers, steals, and defensive rebounds. And I click on graphs. Like last week, I want to do some residual diagnostic. So I want to have output of the 4-in-1 graph. Basically, this is what I get. I just did this again just to show you like how I got those kind of outputs. I have regression equation, I have coefficient. Here you see the coefficient, the first columns, just the coefficient before each of my predictors. Have the standard error of the coefficient. The t-statistics, again, is just the coefficient divided by the standard error of the coefficient. The p-value very small, smaller than 5%. So all of my predictors and constant are statistically significant. VIF is a measurement for collinearity. I think you have already covered collinearity, but you don't have to know how to quantify it. It's just like when VIF is relatively small, smaller than 5 or 10 perhaps, like there is actually a hypothesis test to check whether collinearity is a problem. But when the VIF is smaller than 5, I think, especially when your like number of observations, your predictors are large, then a small VIF kind of saying the collinearity is not a very huge problem. – Again, we have the standard error of the estimate. We have the R square and adjusted R square. Um, an analysis of variance, which leads to the f-test and the f-test of the regression. I'm going to talk about it later. But basically the p-value, you see, the p-value from the first row is very small, 0 until the third digit. So basically it says my regression is statistically significant, which reject the null hypothesis that all the betas equals 0. So here it comes to the main point of this session. I'll talk about the diagnostics for unusual observations. Minitab actually gives us an output about unusual observations. And here we see we have two unusual observations, which are observations number 7 and number 27. I can look at my original data. Number 7 is Dallas Mavericks. Number 27, San Antonio Spurs. Those two observations were flagged unusual by Minitab, but let's see like how unusual they are, or like what kinds of unusual data point they have. So basically they marked R, and here Minitab had an explanation. R means large residuals, which in other words they are potential outliers. Sometimes we have like another kind of flag. I don't know like which letter it stands for, but it also Minitab also marks high leverage, right? So basically, this output gives us all the points which are potential outliers, and also points that are potential leverage points. But here, I only have outliers, right? All of my observations, according to Minitab, do not have a very high leverage. But what does this really mean? First, we want to check the assumptions of the linear regression model. Our errors are normally distributed. Well, I think according to the histogram and the QQ plot of the residual, it seems my residuals are sort of normally distributed. And since residuals are the best predictors for the errors, I kind of agree that the normally distributed error assumption holds. Something I need to notice is here on the normal probability plot, the upper right corner, here's I have a point which Minitab shows it's a row 7, have a residual of 16.67. That is actually sort of an outlier that we just discovered. Row 7 is our 7th observation. Remember, Minitab gives two outliers, row 7, row 27. It means here the residual, most of the residuals are kind of lie on the red line, despite this one. So basically it has a abnormal residuals. We can find it on the second graph, the row 7 graph, right? The residual here, it shows 16.67, right? And you can see it like on the y-axis, the residual axis, it's more than 15. Actually, it's like 16.67 sort of thing. It's a hint of outlier because in the residual plot, I have like a very high residual, which means my predicted y and the actual y has a very large difference. And if I draw the line of best fit, then I'll see my seventh observation actually derives from the line of best fit, actually much higher than the line of best fit. And their vertical difference is 16.67. And remember, from the Minitab output, I have two outliers, right? The observation number 7 and observation number 27. From this graph, I can actually locate, maybe better from the residual versus observation order. From this graph, I can actually locate where's my 27th observation, right? Here, it's the 8th observation. It's a 7th observation. And this point is actually our 27th observation. And we see it has a very low residual. By the way, it coincides with this point on the residual versus fitted value plot. It's lowest residuals. So the bottom line is when you do the residual diagnostic, you look at the residual plot, and basically if there is an excessively large or small residual, then it could be an outlier. An outlier is your outlier means your actual y value is far away from the predicted y based on the linear regression model. The way to quantify the residual is like to quantify outlier. Basically, I'm doing the same thing, but for the 4-in-1 graph, I click instead of regular residual plots, I use a standardized residual plots, and it converts my residuals to standardized residuals, and I'm plotting against a standard normal distribution. And the good thing is when you like check outliers from like a normal distribution, what you're gonna do is you want to check if a certain observation lies 2 standard deviation away from the mean. And the mean is 0 for the regression, right? And by standardizing the residual, the standard deviation becomes 1 because the standard normal distribution has a standard deviation of 1, right? So 2 standard deviation away from the mean is actually 2 in absolute numerical value away from the mean. And from this plot, we can easily see this point, our 7th observation, right? You look at the corresponding y-axis, it's more than 2. The 27th observation, you look at the corresponding y-axis, it's less than -2. So according to Minitab, those two should be outliers. There's no a strict rule of like how many standard deviation away corresponds to an outlier. Some people say maybe 2 standard deviation is a good measure, and Minitab uses this number, and it flags all the points whose residuals are greater than 2 standard deviation from the mean, or greater than -2 standard deviation from the mean. Sometimes I use 2.5 This is just exactly the same data I am using. If I use 2.5, then my conclusion might be there's no outliers at all, or maybe only our seventh residuals corresponds to an outlier. If we look at this point, has a residual of 2.48, right? Very close to 2.5. So basically this point is still worth discussing, worth studying, because even I use 2.5 standard deviation away from the mean as a cutoff point, it's still very close to that cutoff. So this is the um, outlier. The bottom line is outliers are points which derive from the line of best fit. Its actual y value and its predicted y value based on linear regression model have a very large difference, and we call that difference residual. It has a very large residual. Then I talk about the leverage point. I'll talk about the leverage point and the influential point at the same time. Here I can actually storage the leverage and Cook's distance. It has sort of a formula to calculate leverage and Cook's distance, and I wrote them down here. The leverage point. Basically, leverage points are observation which have an unusual x value, a very huge x value or small x value, and here the x is a collective x, right? Because I have several predictors. It's a multiple linear regression model. If, for example, all of my predictors are very, very large, then it is very likely to be a leverage point. But the way we see, right, in the numerator, xi minus the mean of x, and square it, right? If my xi derives from the mean of x, either very large or very small, right? That difference in absolute value should be large, and you square it, it should be very large. Basically, if I get a very large HII, that means this point should be a potential leverage point as a very high leverage. So I have already done that. Basically, the column C14 is my residuals, the column C15 is the HII, column C16 is the Cook's distance. By the way, the formula for the Cook's distance is here. Again, if you get a very large Cook's distance, if it's larger than 1, then it means my specific observation is an influential point. So I can actually plot a time series plot of the residuals of the leverage and the Cook's distance, like I did here. The residuals I already done that. The time series plot is just the standard residual versus the observation order plot. But I also want to plot like the leverage versus observation plot of the leverage and the Cook's distance. The Cook's distance y-axis and observation order on x-axis. I don't think like you really have to replicate my steps, right? In your homework, you just want like all I expect you to do is you just observe some large or small residuals, observe some large leverage or Cook's distance, right? You don't have to actually do a hypothesis test to determine if it is really large enough to become a leverage point or to become an influential point. You just need to point out. And by the way, the Minitab actually, right, as I showed you, gives me already gives me a diagnostic observation output. So it's very convenient. But what I can do is I go to stats, I think time series plots, and I can plot, for example, my leverage against my observation, and comes this graph. There's actually a hypothesis test, like, because for example, this point have a very high leverage, maybe have a very high leverage. It has a HII of close to 0.4, but is that high enough? Right, so there is actually a hypothesis test, which is if my HII is greater than 2.5. Again, I'm using 2.5. Some people use 2, some people use 3. I don't know what points, I don't know like what value Minitab uses, but my answer here agrees with Minitab. If I use 2.5 and times the number of predictor plus 1, here I have 5 predictor and 30 observations, right? There's 30 MBA teams in total. If I use this, I get a number of 0.5. So if all the points, all the leverage, they less than 0.5, then it means my observation actually does not contain a leverage point, which coincides with the result that Minitab gives me. Remember, Minitab just gave me like the 7th observation and 27th observation as outliers, and there's no leverage point. So basically here, I agree with the Minitab. For the Cook's distance, I can do the same thing. I plot a time series plot of Cook's distance on y-axis, observation order on x-axis, and the hypothesis test is basically if all of my Cook's distance is less than 1, then it means I do not have an influential point. I think those methods, like all of those methods, you don't have to use all of them, but they will be useful for you to do the first question of the homework. It's not due this week. But basically what you can do is you can look at the output of the Minitab, which gives you directly the outlier and leverage point that Minitab thinks. I don't know like which number Minitab use, right? I'm using 2.5. And then you can look at the residual plot, right? You can identify the excessively large and small residuals. You can convert the residual plot actually to a standardized residual plot. So you just need to identify the residuals which standardized residual plot like this, right? You just need to see if the y-axis is greater than 2.5. That's the number I'm using. You can use 2, right? So this number Minitab uses 2. This number is greater than 2. This number is less than -2. So those two numbers, according to Minitab, outliers. And for the leverage, you can plot the leverage as I did here, right? I show you the steps again. Go to stats regression, those are the old things we were doing many times. Click on storage, and I click leverage, and I click OK. At storage, the leverage. If I could click Cook's distance, maybe the residuals, and I click on OK. That gives me 3 columns, as I showed to you. The last 3 columns. C14 is my residual. This is my leverage. This is my Cook's distance. And I showed you the formula. And by the way, the HII, the C15 column is just the diagonal entries of the hat matrix. It involves some linear algebra stuff. You don't really have to understand it. But the bottom line is you have to understand like what is an outlier, what is a leverage point, what is an influential point, and what Cook's distance measures. The Cook's distance measures the influential point. From this example, I don't have influential point. Actually, all of my Cook's distance, the highest one is just a little bit above 0.2. It's not even close to the cutoff point of 1. But that's the bottom line. From this exercise, I hope you could understand like what's the meaning of the outlier, the leverage point, and the influential point. And you got to know like what's Cook's distance measures. Then I move on to the next topic, the F-test, which is actually your second homework problem. Here's the slides when I took this class. Here's the slides I didn't have your slides by now, but so I'm using this one. From this output analysis variance, look at the first row. That's the regression with a p-value 0, and it has an f value. That f value comes from the f-test. Basically, my null hypothesis is all the betas equals 0, like none of my predictor actually help to predict the response. In my example, the win percentage, like none of my predictor is helpful to predict the win percentage of the NBA team. So in a technical term, I wrote like our null hypothesis is beta 1, beta 2, all the way to beta k, assuming I have k potential predictors and they all equals 0. So that's my null hypothesis. And the F statistics, here is the formula. The sum of square of the regression over k divided by the sum of square of the error over n minus k plus 1. In F table, actually when you want to find the critical F value, you need to have 2 degrees of freedom. The degrees of freedom in the numerator, which is k, and the degrees of freedom in the denominator, which is n minus k plus 1, n minus parenthesis k minus k plus 1. That's the 2 degrees of freedom you have to know. The SSR and SSE from the formula sheet I prepared last week. You know what is SSE and SSR. It's just, and by the way, those are also correlated with R square, right? You have this magical formula, the total sum of square equals the error sum of square plus the residual sum of square. And in exam, all of those numbers should be given. You don't need to actually calculate the sum of all the difference of yi and the predicted yi and square them. It's not practical to do it by hand. So basically I have my F statistics and I want to compare my F statistics with the critical F. The critical F, you need to look at the table, right? With the degrees of freedom in the numerator being k, and k is the number of predictors you have, and the degrees of freedom in the denominator, the n minus parenthesis k plus 1. And if your F statistics is greater than the critical F, then you're gonna reject the null hypothesis. Right, your null hypothesis is all the betas except beta 0, like all the other betas equals 0. None of the predictors is helpful in predicting y. But if you get a very large F statistics, you're gonna reject the null hypothesis, saying there's actually some predictors, maybe 1, maybe 2, maybe k. You don't know how many predictors from the F test, but at least one predictor is useful in predicting your y value. That's the F test. Here I forgot one thing. I want to show you how outliers, influential points, and leverage points undermines the regression model. So here's a simulation done by Professor Simonoff. Basically, I have a lot of observations. I didn't remember like how many observations we have, but you see like the majority of the observation clustered at the upper left corner, and it definitely shows upward trending. However, there's one observation which I can definitely tell you without doing any hypothesis test is both an outlier and an influential point and leverage point. And by the way, if a point is both an outlier and a leverage point, then it's very likely to be influential. So that means if you calculate the Cook's distance, it's very likely to be greater than 1. And you'll see like how outliers and leverage points can undermine the regression. I did like an ordinary least square regression, multiple. I think multiple. It should be a simple linear regression maybe. Did that regression analysis. I fitted the regression line, which is the red line, using the least square principle. And you see my line of best fit actually have like a downward trending, which totally like undermines what actually happens. In reality, there should be a story lying behind this outlier and leverage point, right? Must something going wrong. And in practice, what we're gonna do is we're gonna omit this point, and we do a regression model based on all the other observation, and I get a red line basically with the upward trending. That's what actually happening. But with this outlier, all of my model just being undermined, very hugely
Hello?
undermined.
Hello?
Oh, yeah. Today I'm talking about the leverage point, the outlier, and the
Hello,
influential
Victor?
point. I'm very close to finish all of them. Um, And I would say if you have any question, uh, just give me like 10 more minutes. I finish everything
Hello,
and you can ask your question. Is that fair?
Victor.
All right, so here I'm just talking about how um, outlier and the influential point could totally undermine the regression. And you can see like what actually happening is I have an upward trending. However, with one specific observation in the down right corner, um, my line of best fit actually have a descending trend. So that's very, very bad because the linear regression model is very sensitive to outliers and leverage points.
Hello, Victor.
Yep. Can you hear me? Oh, I think cannot hear me. I don't know what's happening. All right, so I continue talking about like your homework number two. Here I have already answered like the first two questions of your homework number two. You're gonna this is a form of R square. R square. This is just the formula like you can find in the formula sheet. I think R square, right? R square is SSR divided by SST, and SST is SSE plus SSR. Um, so so here's the R square and F statistics, which I just talked about. And then based on these two formula, you're doing some basic algebra and you're gonna prove the equation that appears on the part C of your homework. Just these two formula. And you have to know like the total SST. SST equals SSE plus SSR, and you have your F statistics, and you just play with some algebra game. It's not very difficult. And you get the formula from the part C, and basically you can use that conclusion to do the rest of your work. I think after part C, you are given like two examples where you're gonna calculate, you're gonna do the F test and see if the null hypothesis of all the betas except beta 0 equals 0 holds. Um, you can use the conclusion from part C. Mm. One last thing I think is very important is the partial F test. The F test, like I'm not gonna talk about it in detail today. I'll talk about it next office hour, maybe. This one is very, very important. The difference from the F test we just discussed and this one is like the last F test, the null hypothesis is all the betas except the constant, except beta 0 equals 0. Here, I have a different scenario where I can either use a full model. For example, I have 5 predictors. I can either use 5 predictors or maybe I can just use 4 of them, or maybe 3 of them, or maybe 2 of them, which could be suffice. And remember, it's not true that more predictors are better, because sometimes with too many predictors, you actually um, doing something called overfitting. that you sort of think you discovered something that in reality doesn't even exist. It's called overfitting. So there's a trade-off, right? More predictors you use, the more like stronger your regression becomes. Stronger in terms of you have a larger R squared. However, more predictors can also lead to overfitting. So there's a cutoff. In this example, we're interested in fitting 5 predictors or fitting only 1 predictors using beta 1 only, use the first predictor only. And here to like determine which model is preferable, we're gonna do a partial f-test. The formula is here. And the lowercase omega stands for the simpler model, in this case the one predictor model, and the uppercase omega stands for the full model, in this case the 5 predictor model. So basically you're going to use the sum of square of the error of the simplified model minus the sum of square error of the full model over p minus q, where p is the predictors you're using in the full model and q is the predictors you're going to use, number of predictor you use in the simplified model. In this case, p equals 5 and q equals 1. And in the denominator, you have the sum of square of the error of the full model over n minus p minus 1. N is the number of observation. P is the predictors you use in the full model. In this case, I have 30 observations in total, and p equals 5. So 30 minus 5 minus 1, I get 24. And I can get my F ratio. Again, to get your critical F value in the table, you need to have 2 degrees of freedom. The degrees of freedom of numerator is p minus q, in this case 4. The degrees of freedom in the denominator is n minus p minus 1. In this case, is 24. So you're gonna locate the critical F value by looking at F with 4 and 24 in the table. If your F statistics is larger than the critical F value, then you're gonna reject the null hypothesis. Null hypothesis, remember, is I'm gonna use 1 predictor model over 5 predictor model, and that means all the remaining 4 predictors, they actually equals 0. They are not helpful in predicting my y value. So my null hypothesis in technical term is beta 2 equals beta 3 equals beta 4 equals beta 5 equals 0. The remaining 4 predictors are not useful. That's my null hypothesis. However, in this case, I find a f value which is relatively large. If you put this in calculator, like if I just googled f calculator, I think it's here. So the degrees of freedom in the numerator, the 4, the degrees of freedom in the denominator, 24, f statistics, f statistics 5.64, and I get my p-value 0.00238. Like, you're not gonna locate this p-value in the table, because in the F table there's only some very important p-value, like 5%, 2.5%, 1%, something. But if you just Google an F calculator, you get this one, which coincides with this 0.002376, approximate to 0.00238. Right, this p-value is very small. If you look at the table, the critical F should be very small, should be smaller than 5.65. So you're going to reject the null hypothesis. which means I'm gonna use the 5 predictor model instead of the 1 predictor model. Here in plain English, it means the larger model is preferable to the one only use elevation as predictor, which is the 1 predictor model. Perhaps I'm gonna talk about this again in next week's office hour, but this section I think is very important, both for you to do your homework and for you to get a better performance in the final exam. So that's all, and good luck for the homework.